Good morning, students. In the last class, we completed the first part of the chapter ray optics, that is the phenomenon of reflection and refraction. In the today's topic, we are going to discuss about the second part, that is optical instruments. So, optical instruments are the instruments or devices which are constructed by using the reflection and refraction properties of mirrors, lenses, and prisms. So, these are the devices which are used. These devices are used by using reflection and refraction properties of lens, mirrors, and prisms. By using the properties of reflection and refraction of lenses, mirrors, and prisms, we design the instruments. That instruments we call as optical instrument. In such instruments, that is, some examples are periscopes, binoculars, microscopes, telescopes, are some of the examples of the optical instrument. So, in our syllabus, we have microscopes and telescope, the principle and working of microscope and also the telescope. So we shall study in detail by one by one. So in the starting, first one is microscope, or simply we call this one as magnification or magnifier. So what is microscope? So microscope is the optical instrument. So this optical instrument is used to see the larger images of the point size objects. So what is microscope? Microscope is the optical instrument which is used to see larger image, large image of point size objects, of point size objects. So what is microscope? Microscope is the optical instrument which is used to see the larger image of point size objects. So this is the definition of the microscope. Then how microscope works? So the principle of microscope. Let's study in detail. Before going to study the principle of microscope, so one term is there, that is least distance of distinct vision, that is LDDV. So what is the meaning by the least distance of distinct vision? So before going to study the principle of the microscope, first we have to know this one, that is the least distance. Least distance is nothing but the minimum distance. The minimum distance to see the object clearly by our eyes without straining to our eyes. So that distance we call as least distance of distinct vision. That is the minimum distance that the observer can see the object without straining to the eyes. That distance we call as least distance of distinct vision. So it is denoted by letter D. So least distance of distinct vision is that if the observer is here, that is our eyes are here, if we place one object somewhere here, so he can see the object from here like this, right? He can see the object here at certain distance, that is if it is at 5 centimeter, then he also can see the same object if we place at 10 centimeter, or if he placed at 50 centimeter, the observer can see the object, but he can see the object clearly without straining to his eyes at a distance of 10 centimeter. That is, if we place the marker in front of if we took towards our eyes, it becomes very strained to see the object. So the minimum distance. So this one is the minimum distance. The observer can see the object without strain to our eyes. So that distance we call as distinct vision. After the minimum distance, you can see the object without any strain. But this one is the least distance. After the minimum distance, if we place somewhere here, so the observer eyes can strain to see the object. So that one we call as distinct vision. That is the minimum distance. So we can easily observe or easily see the object at certain distance. That distance we call as minimum distance. After that also you can see the object clearly without any strain. But in before the minimum distance, if we place the object, so the eyes becomes very strained. So that's one we call the least distance of distinct vision, that is denoted by D. The simply we call as distinct vision or least distance of distinct vision. So least distance of distinct vision is defined as the minimum distance that can see the object by the observer without any strain to the eyes. That one is the definition of the least distance of distinct vision. So if we place one object here, so here is the observer. From here he can see the object clearly without any strain. The height of the object we taken as HO. So this is the height of the object. So this object can see by the observer without any strain. Then the object is at a distance D from the eye. That is least distance of distinct vision D. So the principle of microscope. So why we are going to use the microscope is the large size of the image we have to see of the point objects. Here we are not placing any optical instrument between object and to the eyepiece. So this one is the object. Here I will take A, B. So AB is the object. In between object and to the eye, there is no optical instrument we are placing here. From our normal eye, we can see the object at a distance D. Next, in the second step, we are placing the optical instrument. That is, we are placing the convex lens in between the object and to the eye. So, in the first step, if I write here, in the first step, no optical instrument is placed in between object and eye. So in the first step, we don't place any optical instrument here, that is lenses or mirrors or prisms like that. We are not placing any object in between the object and the eye. So in the second step we are going to place one convex lens between the object and to the eyepiece. So this one is the convex lens one is the principal axis. Here is the first focal point. So the eye is always nearer to the lens. So eye is almost nearer to the lens. Right? So how we have to place the object here? Here we are going to place the object in between the focus and optic center. Here we are going to place the object in between focus and optic center. If we place the object here, that is what the object we are taking here. If I place here, that is height of the object h0. If we place the object in between F and O, the image we are getting is virtual, erect, and it is magnified. Magnified means larger in size. So the principle of the microscope is we have to see the larger size of the image of the point object. Here we consider this one as point object. The object size is less. Then we have to, by using the microscope, we can see the larger size of the image of the object. So the image is virtual and the image is erect and it is magnified. By using the rays as we use in ray diagrams, that is image formation in convex lens. Here we are going to take two rays. To find the image of an object, we have to take two rays. That is, one ray is parallel to the principal axis and another one ray is passing through the optic center. If the ray is passing through the optic center, it won't deviate. That is, it goes straight without any deviation. Then this one becomes the refracted ray. This one becomes the refracted ray, and the incident ray that are coming from the object which is parallel to the principal axis. So that refracted ray is always passed through the focus. So this one is the focus of the second point. So if we draw these two refracted rays backward or extend backward, we get the image. That is, these two rays are diverged from the single point. So here we are going to extend or produce back the refracted rays. So somewhere here these two refracted rays are diverged from this point. So this point gives the image of the object. So if we draw the image, so this becomes the image. So this one is the height of the image. So the height of the image is virtual and it is erect and also it is magnified. So if you observe the height of the object and to the height of the image, so height of the image is larger to the height of the object. So this is the ray representation of the microscope. So the first condition is we have to place the convex lens in between the object and to the eyepiece. That is, object and to the eyes in such a way that the object lies between the focus and to the optic center. To find the image of the object, we are taking two rays. That is, one ray is parallel to the principal axis and another ray is passing through the optic center. If the ray passing through the optic center, the refracted ray goes straight without any deviation, and the ray which is parallel to the principal axis is always passed through the focus, that is second focal point. If we produce backwards, these refracted rays are diverging from one point. That point we call as image of the object. That is here A dash, and here it is the B dash. So A dash, B dash is the image of the object A, B. So this one is A and this one is B. So next we are going to find the magnification. That is linear magnification. Linear magnification. Here we have two cases. That is, the image is obtained nearer to the eye. That is, from here we are observing the image of the object. So image is formed at near point. First condition, that is first case. We consider it as first case. In first case, image is formed at near point. So the image formed by the object here, so this image is clearly visioned by the eye. Clearly the eye can see this object. So this distance we are going to take as D, that is least distance of distinct vision. So this distance we are going to take as D, because the eye can clearly see the image without any stripe by using the convex lens. So when image is formed at nearer point, so the linear magnification M, that is equals to height of the image to the height of the object. We know that the magnification of the lens M is equals to ratio of size of image to the size of the object. So if we write in terms of distances, object distance and image distance, in terms of object distance and image distance, it becomes V divided by U. So magnification can be written as V divided by U. From lens formula, we have 1 by V minus 1 by U, that is equals to 1 divided by F. So F is the focal length of the convex lens. So we need 1 by U. So if we shift to origins, it becomes plus. So 1 by U, that is equals to 1 by V minus 1 by F. So now we substitute the value of 1 by V to the magnification. That is M is equals to V into the value of 1 by U. That is 1 by V minus 1 by F. So the value of 1 by U is 1 by V minus 1 by F, that is from lens formula. Now if we simplify further, that is multiply V to the inside the bracket V divided by V, it becomes 1 minus, it becomes V by F. So here this is the image distance. So this image distance will be taken as D, that is least distance of distinct vision. That's why if we apply the sign convention, So always the image distance is measured from the optic center. It is opposite to that of the incident ray. That's why we are taken B is equals to minus D. So then magnification M becomes, so magnification M becomes M is equals to 1 minus of minus D divided by F, that is M is equals to 1 plus D by F. So this is the magnification of the microscope when image is formed at nearer point. When the image is formed at near point, we have to remember this formula. M is equals to 1 plus D by F, where D is the distinct vision, least distance of distinct vision, and F is the focal length of the convex lens which are used in the microscope. So this one is the first case. In the first case, we are taken image is formed at the near point, then we have the magnification M is equals to 1 plus D by F. Next, we are going to study the second case. So what happens in the second case? The second case is the image is formed at infinity. In second case, we are taken image is formed at infinity. So when we get the image is at infinity, we get the image is at infinity when the object is placed on the focus. If we place the object on the focus, then we get image is at infinity. So this one is the second case. So when the object is at focus, we have to calculate the magnification. So if I write here the second case, in second case, the object is placed at infinity. Same values here. Principal axis, it is focus, and here we have eye, and here is the optic center O. So the condition for image has to be formed at infinity. This object AB is placed at the focus. So here we are placing the object. That is object AB is placed at the focus. Now we have to find out the image formation. Here also I am considering two rays. One is parallel to principal axis and another one is passing through the optic center. After refracted by the first ray, it goes through the focus of the second point. Here we observe means these two rays are parallel. If we extend these two parallel rays, they will never meet because parallel lines are never intersect. Hence, the image is formed at infinity. Now these two rays becomes parallel. So if we observe here, the refracted rays are parallel. If we produce backwards, these two rays are parallel. That is, these two rays are never intersect. Then the image is formed at infinity. So this distance we have taken. The object is placed at focus. That is, the object distance is at. So this one is u, and also the distance between optic center and to the focus we have taken that one as focal length f. That is, object distance is equals to the focal length of this mirror. To find the image at infinity, we have to place the object at the focus. Then the object distance and image distance are equals. Next, here we have one term, that is angular magnification. In previous case we discussed about the linear magnification. So when the image is formed at infinity, we have not linear magnification, we have angular magnification. So what angular magnification says, it is the ratio of angle formed by the image at infinity. That is, angle, it is the ratio of angle formed by the image at infinity to the angle formed by the object at the angle formed by the object at least distance of distinct vision. So this one we tells that the angular magnification. So angular magnification is the ratio of angle formed by the image when image is at infinity. That is this angle. That is angle theta. The angle formed by the image at infinity. So here somewhere the image is formed at infinity. So this angle, the rays which makes angle with the principal axis, that angle we call as angle theta. That is, angle theta is obtained by formed the image when image is at infinity. Next, the angle formed by the object at least distance of distinct vision. So this one is the angle. So that one we are taken as theta naught. So this one we gives the angular magnification. So m is equals to theta divided by theta naught. So this is the angular magnification. This angular magnification is also called magnifying power. Magnifying power. So angular magnification or magnifying power. It is the ratio of angle formed by the image at infinity and to the angle formed by the object at least distance of distinct vision. So from observing the first figure and the third figure, if we observe here from this figure, we can write tan theta naught is equals to h naught divided by d. Tan theta naught is equals to h naught divided by d, opposite side by adjacent side. So considering for small angles, theta naught becomes, that is, tan theta naught is equals to theta naught. That's why theta naught is equals to height of the object to the distance d. So this is first one. From this figure, the object is at infinity, theta is equals to, the image is at infinity, here the distance tan theta, that is equals to angle formed by the object. Here is the, sorry, angle formed by the image tan theta, that is equals to height of the object, and to the, this one is the distance opposite side by adjacent side, that is it's not divided by u, or we can take it's not divided by f. For small angles it becomes theta is equals to h naught divided by f. So if we substitute the values of theta naught and theta to the magnification m, so we get the value of theta is h naught by f whole divided by h naught by d. So in the numerator h naught and in the denominator h naught get cancelled. So if we rearrange, then the angular magnification or magnifying power m is equals to d divided by f. So this is for the image which is formed at infinity. So this is the angular magnification when the image is formed at infinity. So if the image is at near point, we have magnification m is equals to 1 plus d by f. So in the first case, the linear magnification m is equals to 1 plus d by f. So in the second case, when the image is at infinity, the angular magnification or magnifying power m is equals to d by f. So these are the two cases which are we study in the microscope. One is nearer and another one is at infinity. So this is about the microscope. So what is microscope and what is least distance of distinct vision, and how we obtain the image, and the principle of microscope, and the magnification in two cases. One is image formed at nearer point and second one is image formed at infinity. So this is about the microscope. That is microscope or simple microscope, because here we are using only the convex lens. The main principle of using the microscope is to obtain the image, to obtain the image, to obtain the image, to obtain the image virtual, erect and magnified. To see the clear image, we have to magnify the point size objects. So while seeing through the lens, so eye is nearer to the lens. So this is the condition, and why we are going to use the microscope is to find the magnified image, to find the magnified image of the point size objects. So this is about the microscope or simple microscope. This one we call as simple microscope. So next one is compound microscope. So next one is compound microscope. So why we are going to use the compound microscope? Already we have the microscope, but also we constructed the compound microscope. compound microscope. Here the principle is, the main aim is to get the enlarged size of the image of the point size object. So we have one drawback of the simple microscope. From this relation, that is f is equals to d by f, to increase the magnifying power, of the simple microscope, we have to decrease the focal length of the lens, that is focal length of the convex lens. If we decrease the focal length of the convex lens, then only we can magnify, that is we can enlarge in the image, because here f is inversely proportional to magnifying power m. So if we decrease the focal length of the lens, then we get the image. So the image is not clear. If we decrease the focal length of the convex lens, the image is not clear, but it is enlarged, but the image is not clear. It is blur in color, that is blur in nature. To increase the magnification, we have to insert another lens. So for compounding one on another one, that's why the microscope is called as compound microscope. To overcome the drawback of the simple microscope, we constructed the compound microscope. So in simple microscope, we used only one lens. To overcome that one, in compound microscope, we placed two lenses in between the object and to the eye. So this one is the main drawback of the simple microscope. That is, to increase the magnifying power, we have to decrease the focal length. So it is not, if we decrease the focal length of the lens, we get the image which is not clear. That's why we are using the compound microscope. So let's see how compound microscope will work. So here we are taking one lens. This is the principal axis, and here taking another one lens. So these two lenses which are placed in between object and eyepiece. This one is the object, and here is the eyepiece. This is the eyepiece. As like in the microscope, we have placed in between object and eye only one convex lens. So here we have taken two convex lenses of different focal length. If we consider this one as object, this one is the object, that is A and B. So AB is the object. The lens which is placed near to the object, that lens we call as objective. The lens which is placed nearer to the object, that lens we call as objective, and its focal length we taken as FO, that is focal length of the objective. The lens which is placed nearer to eye, that lens we call as eyepiece. That lens we call eye. The lens which is placed nearer to eye, that lens we call as eyepiece, and the focal length we taken as FE. So here FE is greater than FO. The focal length of eyepiece is greater than focal length of the objective. So next we find the image formation. So here is the object. To find the image, here we are going to consider two rays. So one ray is parallel to the principal axis and another one is passing through the optic center. So it goes straight without any deviation. The ray which is passing through optic center, it goes without any deviation. So the second ray which is passing through the focus. So this one is the focal length of eyepiece. And this is eyepiece. So one ray is passing through the optic center O, it goes right without any deviation, and the second ray which is passing through which is parallel to the principal axis, it goes through the focus. So here is the focal point of the second, that is second focal point. So this distance is from optic center to the focus, the distance is f0, that is focal length. That is, this distance is focal length fo, right? As we already discussed, in thin lenses in contact, or we considering two lenses, the image here, these two refracted rays are converging at this point. So at this point we get the image of the object. So this is the image of the object, that is B dash, and here it is A dash. So this one is the height of the image, right? So these considering two rays, one is parallel to principal axis and another passing through the optic center. These two refracted rays are converged at that point. That point gives the image of the object AB. In thin lenses in contact, or we considering two lenses, then the image formed by the first lens acts as the object for the second lens. Here the image, this one is the image, A dash B dash is the image of the object AB. So this image acts as object for the eyepiece, that is for the second lens, right? So this image acts as object for the second lens. So the rays which are coming from the object A dash B dash falls onto the eyepiece and gets refracted. And get refracted like this. From this image, that is virtual object, A dash B dash acts as a virtual object. From this, the rays which are coming towards the eyepiece and gets refracted to the eyes. So if we extend these refracted rays, that is, if we produce these refracted rays backwards, So these refracted rays are diverged from the point somewhere here. So here we get the image of the virtual object. So this one is B double dash and here is the A double dash. So if you observe here, AB is the object, the AB is the object and A double dash, B double dash is the final image. So if we observe these two, the size is very small, the AB is very small and A dash B dash is very large. The image of the object is B double dash and A double dash, that is magnified image. We are getting the magnified image. In the first case, the image is real and inverted. The image is real and inverted. And in the second case, that is for the eyepiece, we get the image magnified. If we see the AB and A double dash, B double dash, so we can easily notice that this image is magnified. So this is the image, right? From the eye, easily we can see the image of the object. So in the first case, we get the image. The image is real and the image is inverted. So in the second case, when it falls onto the second lens, that is for eyepiece, the image we get, which one is the magnified. So next, magnification in case of the compound microscope. So if we take here this point, right? So here the angle is beta, then here also the angle is beta. These two are similar angles. In case of I am taking angle beta, I am taking angle beta because the AB is equals to, if I take N, this point as N, the AB is equals to NO, that is NO is equals to H naught. So here the angle is same. At the point F, we have angle beta, that is opposite here, that's why here also we get the angle beta. So from triangle NOF, we have tan beta, that is equals to opposite, that is NO is the opposite side and OF is the adjacent side. Here these are the parallel rays, then AB is equals to NO, then NO is equals to H naught, that is equals to H naught divided by, where OF is the focal length of the objective, that is F naught. If we considering the angles are small, then beta is equals to H naught by F naught, then H naught, that is height of the object, H naught is equals to F naught into beta. So this one is the focal length of the object. So somewhere here, this one is the focal length of the eyepiece, as FE is greater than FO, and the distance between here, the distance, if you observe here, you find this distance we call as L. So L is the tube length. L is the tube length, which is the distance between objective focal length to the eyepiece focal length, that is FE and FL. The distance between the FE and FL, that one we call as tube length, where L is the tube length. So L is the tube length, right? So next, from triangle F B dash A dash, from triangle F B dash A dash. So this point, the focal length, this one is FE, that is focus of the eyepiece. So this point is nearer to the point B dash. That's why this length is taken as L. So if you draw F is here, if you come up to here. So L is the distance between FO, that is focus of the objective, and focus of the eye lens. So this length we call as tube length. So the L is nearer to, so the focus point is nearer to B dash, then it approximately we taken that length as L. So from triangle F B dash A dash, so we can write tan beta is equals to tan beta, that is equals to opposite side is B dash A dash divided by adjacent side, that is F B dash. So considering small angles, then tan beta becomes beta. B dash A dash is the height of the image, that is HI, and F B dash, so this one we taken as L. So height of the image HI is equals to beta into L. Right? So next, from magnification, that is M is equals to height of the image to the height of the object. That is, this magnification is magnification of the objective. That's why it's taken as MO. So MO is taken as magnification of the object is height of the image to the height of the object. Then MO is equals to, so height of the image is beta L divided by height of the object is beta focal length of the object. So in the numerator and denominator we have same beta, then the magnification of the object to MO is equals to L divided by F. So this is the magnification of the objective. Next, we have to find out the magnification of the eyepiece. As similar to that of simple microscope, we can write magnification of eyepiece in two cases: when image is formed at magnification, here image is formed at near point. So we can write ME, that is equals to 1 plus D divided by F. So when the image is formed at near point, the magnification of the eyepiece can written as 1 plus D by F. So if it is at infinity, the image is formed at infinity, then ME is equals to D by F. For the eyepiece, we have two. One is the image is formed at near point and the image is formed at infinity. Then the total magnification, then the total magnification M is equals to, here we have combination of two lenses, then its powers is equals to summation of the individual powers, and if we take in case of magnification, total magnification, we have the product of magnification of the objective into the magnification of the eyepiece. So here the total magnification in two cases, if we write the image is formed at near point, so we get m is equals to m of the objective is L by f naught into m of the eyepiece, that is at near point. So we can write 1 plus d by f. So this is the magnification at near point in case of the compound microscope. So if we write at infinity, that is image is formed at infinity, the total magnification m can written as L by f naught into me we taken as d by f e. So here it is f0 and here it is fe. Focal length of eyepiece, that is fe. So these are the two magnification, that is total magnification in case of image is formed at near point and also the image is formed at infinity. Okay. So this is about the compound microscope and magnification power, that is total magnification. M is equals to m of the objective into m of the eyepiece. So in the next class we will solve few problems on simple microscope and compound microscope, and next we move on to the topic telescope. Thank you.